Figure at the left is from Bayesian-based iterative method of image restoration, submitted by William Hadley Richardson in 1970. Richardson was on the staff of the Visibility Laboratory of the Scripps Institution of Oceanography. Scripps was founded by William Ritter, a biologist from UC Berkeley. It became a department of the newly established University of California, San Diego, when that was established in 1960. The Visibility Lab was established at MIT in 1939 and was relocated to San Diego in 1952 as a branch of Scripps. It conducted pioneering research and instrument development in imaging through the ocean and the atmosphere until it was disbanded in 1987. Richardson credits James Harris, who would later briefly direct the Visibility Lab, for suggesting that he explore Bayesian methods. The figure shows two ground truth binary objects here at the top, and then B is the measurement of those that have been graded somehow by the imaging system. Rows C, D, and E show the application of 10, 20, and 30 iterations of a Bayesian estimator. We'll discuss the algorithm in more detail in episode 16. The figure at the right is from a paper by Lucy. Lucy was on the faculty of Columbia University from 1965 to 1986 when he joined the European Southern Observatory. He was a pioneer in the computational analysis of astronomical data. Here's a photo of him later in life. The figure shown here is from his 1974 paper in which he independently derived the same expectation maximization algorithm that Richardson had earlier published. The image shows a particular distribution in the solid line, this psi, and then iterations to try to recover that distribution from a degraded image using the Bayesian algorithm in psi 15 and psi 3. So that's kind of the state of the art of imaging in 1970. Here's an image of Geoffrey Hinton. Hinton received the Turing Award for the development of artificial neural networks. He played a especially pivotal role in the development of backpropagation algorithm for neural training and to the recent development of deep networks. The image shown here does not reflect his own work, however, but rather applies a diffusion model to Bayesian estimation, implementing an extremely advanced version of the EM algorithm proposed by Richardson and Lucy. The image at left is a 64 by 64 low resolution image, and the image at right is a megapixel image generated from the kilopixel input. Comparing this slide with the previous examples, one struck by how far computational image estimation has come in the past half century. Much of the advance is from the improvement in computational hardware, which has improved by many orders of magnitude, but algorithms have also advanced substantially. On the other hand, this diffusion approach is a generative algorithm which can produce results without physical grounding. Here's the high-resolution image that was used to generate this 64 by 64 image that was from which Hinton's image was generated. So this image comes from the ACM website announcing the Turing Award for Hinton. Note that the generated image differs from the high-resolution image in many respects. The lines on Hinton's face are different. There's a mark on his cheek over here in the generated image, which is not in the true image. So there's a lot of things that are introduced by the generative image which are not true to the physics. The goal of computational imaging is to combine image estimation tools with sampling to accurately estimate the object. The next step in the pursuit of this goal is understanding how to invert forward models. Let's get started. Computational imaging. Episode 12, Methods and Metrics. Okay, so we've completed a series of lectures on how to build forward models for computational imaging system. Our course continues now with the discussion of how do we estimate objects from measurements, the inverse problem. After that, we'll get into physical imaging. We'll talk about geometrical imaging systems, wave imaging systems, coherence imaging systems, before we wrap up our discussions by considering details of digital imaging systems, imaging system calibration, and design. The inverse problem section after today will include 5 more episodes focusing on Wiener filtering, linear regression, constrained optimization, Bayesian methods, and neural methods. Okay, so let's reach way back to episode 1 where we talked about the issue of what is imaging. We have an object that gets mapped onto measurements. Objects described by a distribution over the object space, and the measurements are described by a distribution over the measurement space. Often the measurement space is lower dimension than the object space. We represent this system with a forward model that can be initially described by a integration, but ultimately we turn the forward model into a discrete forward model where we have a vector of terms describing the object that gets mapped into a discrete set of measurements, and of course noise is involved in this process. Computational imaging consists of the estimation of f given g. So we're going to start figuring out how to do that. In the grand history, 1,000-year history of artificial imaging systems, there's been 5 basic algorithms for solving this. Number 1, isomorphism. Our estimated scene is the measurement. So this is typically what's done with photography, that we take a photograph and that's our image. But we can do better than that. So the step 2 would be to try linear regression. So we have this forward model that describes how the measurements are derived from the object. So we would try to minimize the regression error between our measurements and the forward model operating on the estimated measurements. Strategy number 3. So the linear regression was, a common strategy from, let's say, the origin of computing in the 1940s and 1950s through the 1970s. Beginning in the 1970s, we have a third approach where we combine linear regression with a prior, with a constraint on the reconstruction. So we both try to minimize the regression error while maximizing the performance of the object, the estimated object, against some prior. And as we'll see, this allows us to fill in some of the missing data from the regression. The fourth algorithm and the fifth algorithm both rely on Bayesian methods. So Bayesian methods is a maximum likelihood estimate, like what we talked about a couple lectures ago when we talk about the Cramer-Rao lower bound. This episode number 4, this is what was derived by Richardson and Lucy, that we treat the impulse response as a probability distribution for the position of the object data, and then we can recursively try to estimate the underlying object from this kind of probability interpretation of the measurements. And then finally, so expectation maximization, as I said at the intro, was developed in the early 1970s and remains a popular algorithm. But estimation maximization Bayesian methods can be implemented on a much finer scale with neural estimators. Neural estimators are not orthogonal to the previous 4 algorithms. In fact, each of the previous 4 algorithms plays a role in initializing what we do with the neural estimator. But a big difference, as we'll see with the neural estimator, is that the neural estimator can analyze the actual content of the scene and build the estimated object based on semantic analysis of the content. So it's a major step up in sophistication, but also the very nature of algorithms changes from a sort of physical model, forward model based approach to an estimator based on the structure of the scene, as we'll see in a few lectures. Okay, so those are the 5 methods is all you need to know. And of course, there's lots of details in getting into them, but we'll review them briefly in the next 5 lectures. Okay, so then how do we tell if it's a good estimator or not? Well, for that we need metrics. And so this is a slide from the last lecture. We talked about image super resolution. And you see here that this is comparing a whole bunch of different inverse problem algorithms. So, we have bicubic is basically a linear method that's here at the upper left, and going down through a variety of different neural estimators. And for each one of the estimators, 3 parameters are given: the PSNR, the SSIM, and the IFC. So PSNR is the peak signal to noise ratio. SSIM is the structural image similarity metric. IFC is a information fidelity criterion. And so those are criteria we can use to evaluate the quality of an inverse model. There are many other criteria, so we just bring this up here to mention that these kind of criteria are the kinds of things people use to compare algorithms. So the error shown here at the upper left, this is the mean square error, where we take the true object and the estimated object and calculate their total difference over the scene. That's the error in the estimator. The PSNR is the maximum of the signal divided by the mean square error. So we need to divide the error by the area of the object to get the mean square error. But if we take the ratio of the maximum signal value to the mean square error of the signal point, take its log 10 multiplied by 20, that gives us PSNR, which usually is expressed in terms of dB. SSIM, we won't get into all the details, but the idea here is to find something that's not, mean square error can be very misleading because you could have error, locally in an image, and then less error elsewhere in the image, and so you can be confused by error values that are not distributed over the structure of the image. So structural similarity attempts to resolve this by looking at the underlying object structure. It uses color images, so L here is a luminance channel, C is a contrast, and S is a structure. Mu is mean values of the two images that we're trying to compare. These constants C are in there just to avoid infinities in these ratios. And then there's a weighted metric you can take over over all these parameters to get the structural similarity, which is usually a number between 0 and 1. This information fidelity criteria is based on a mutual information between the two images that we're trying to compare. We won't get into the details of calculating it here, but we'll just be aware that these different metrics exist. Most of this course is not really going to be, details of reconstruction algorithms or details of these metrics. We're focused primarily on the physical sampling model, the quality of the physical sampling model, and how to use that with different algorithms. But to do that, we do need to apply the algorithms. So we're going to start next time by talking about Wiener filtering. Here we see an example of an original image, the image blurred by sampling with some point spread function, and the Wiener result and the Wiener filtered image to recover the original. And we'll talk about how that works in the next discussion.